Hello, this is a review video lecture. Hopefully it will prepare you for the first midterm exam. In this lecture I will be selecting certain problems from the 3 chapters that you will be tested on, chapter 22, 23, and 24. And I will begin with maybe a couple of problems from chapter 22. The first one that I want to do is number 75. I will be concentrating on, a tougher problem, a little bit harder ones, because I would like to show you how a challenging problem would work out. So I will begin with problem number 75. So let me go to that problem from the book. Chapter 22. And the problem. Before I show you 75, I want to show you, I'm not sure if I have given you number 62 as homework. I don't even remember if I have covered it in one of my video lectures. But let me just, I'm not going to solve it. I'm just going to go over it because it's very similar to it, this one here. Have you done that? Let me go over it very quickly. It is kind of a preview to number 75. Also, number 67 or 68. I am sure that I've done one of them in one of the video lectures. This one, I don't remember which one, 67 or 68. Again, those two or one of them are also related to 75. 75 is actually a combination of those two problems, the 67 and 62. Let me go over 62 very quickly. It basically said, let me get it magnified. Oh, it's the highest magnification we can go. All right, so basically what you have, let me just read the problem. He said you have two masses here, both charged with 100 nanocoulomb each, or both positive. They are hung from two strings up to a pivot here in the ceiling. Because of the like charges repel, so they will repel each other at some distance r. It's not given to us, and the masses are given to us and the charges are given to us. He said 2 5-gram point charges on a 1 meter long threads repel each other after being charged to 100 nanocoulomb. All right, he's asking for the angle. Okay, I'm going to give you a sketch of how to solve this problem. And then I'm going to move on to the next one, to number 75. So here's how it goes. So number 62. Okay, so what you have is so you have those two, I'm going to call them masses if you don't mind. There we go. Both positive, doesn't matter, they could be negative both. And then the mass of each is 5 gram. And then the charge on each, we'll call it Q, is 100 nanocoulomb. And as a result of that, so they are repelling each other at an angle. I don't know, is the whole angle theta or one of them? Sorry. Okay, so you have theta, okay, so like that. And the distance between them is not given to us. And he wants to know, so this is Q, this is Q, this is M, and this is M, masses. And he's asking us to find theta, okay? So the way you do it is the following. You take one of them, and then you draw the free body diagram on it. I'm going to take, let's say I want to take the left one. You could take the right one, doesn't matter. So I'm going to take the left one. So what I have is something like that. Here is the mass. Here is the tension. That's not a good picture. Hold on. Here's the tension right there. Kind of exaggerated, but I hope it's okay for you. And then, of course, here is the angle, theta. And then, of course, we have mg. Basically what I'm doing is I'm drawing all the forces on that mass, okay? So I have the weight of the weight of the mass, and I have the tension in the core, just like that. Look at the diagram above. Here we go. Here's the tension, okay? And then, of course, you have as well the repulsion force, the Coulombic repulsion between the two masses. You see what I'm saying? And that Coulombic repulsion should be in this direction. So here it is. I'm going to call it F for now. There we go. So that's the FBD. This is the free body diagram, right? And what I want to do now, I want to resolve things into components. So I'm going to, the T here becomes T sine theta. Then I have here T cosine theta. And so, of course, the whole system is in a static situation. So that means equilibrium. So sigma fx equals 0. I'm going to leave a little space. Sigma fy also equals 0. And the fx is going to be, what is it? T sine theta minus f equals 0, the equilibrium, right? And then for, let me call that equation 1. I like to box equations. And then equation in the y direction, that's going to be T cosine theta minus mg equals 0. Call that equation 2. Of course, I'm not interested in the tension, so I want to eliminate it from both of them. So I look at equation 2. I can solve for T to eliminate it, basically plug it in back into equation 1. So T in this case is going to be mg over cosine. And then take that and plug it back into 1. And that will give me mg tan theta minus f equal 0. Is that okay so far? And, oh, I know, I think I did this problem before. I just remembered, because when you get that theta cubed or something. It's all right. I'll continue on just a little bit more. Now, the next step is, of course, he wants to know the angle theta, this angle here. And, of course, the force here is the Coulombic force, so that's going to be K Q squared over the distance between them squared, correct? Remember, R here is this distance between the charge here and here, so that's going to be R. And then all I need to do is to get an expression for it. So here I have 1 meter here. So let me draw this triangle right there and draw it down here. I'm trying to find an expression for the R. So if this is 1, this is the angle theta, that's what I'm seeking. That would be R over 2. And of course I can use sine, so that's going to be sine theta equals R over 2 divided by 1. And therefore R equal to 2 sine theta. And then you take that and plug it back in here, and then you plug that in there, and then you work it out. Anyway, I'm almost sure that I have done this problem in details in the video of chapter 22. But that's how you do it. Okay, this is just a quick reminder on how this works. I'm not going to go over problem 67 or 68. I don't remember which one I did. They're very similar. But again, we will assume that you have already reviewed that. So now let me jump to number 75. Because 75 is kind of a combination of those two. Okay, so let me go to the book, show you how that works. Number 75. Right here, it's level 3, as you can see. It's not terribly hard, really. But anyway, here is how it works. So he said 2 identical small spheres. So we have 2 balls here, 1 negative, 1 positive. Okay, are charged plus 100 and minus 100 nanocoulomb. They hang as shown in a, well, we have an electric field, 100,000 Newton per Coulomb electric field. Now he's asking for the mass. Okay, let me draw it and then we'll discuss it. Okay. So what you have is the following. So I have one is negative and the other one is positive. And this is 0.5 meters, 0.5 meters as well. I'm copying all that information for my book, for my hard copy here. And then the angle here between them is 10 degrees each, okay? And then you have an electric field. Let's go back to the book. You have an electric field. Let me get the book a little bit. Right here. Okay, so you have the electric field going from right to left like that. You see the pink colors there. So I'm going to just put them here. So you have an electric field going this way on the entire system. See what I'm saying? So this electric field is equal to 10 to the 5th Newton per Coulomb. There's no need for the vector, otherwise I'm going to have to put a unit vector. There we go. Okay, the magnitude of it. And this is the charge Q, and Q here is equal to 100 nanocoulomb. Okay? And then he's asking, what is the mass of each? They're both identical, you see what I'm saying? So what is the mass of each? Here is how it works. Ask the question, what are the forces on either of them? All right, let's pick the plus one. Here is the plus one. Well, I have the first thing the first thing that comes to mind, because I have a string, so there will be a tension right there, T. And I have mg, correct? The weight of the mass, the weight of the mass, the weight of the wall, whatever you call it. And I have two Coulombic forces here. Two, not one. Well, one Coulombic force due to the electric field, right, which is QE, and the other one is a Coulombic force due to the attraction between the two charges. You see what I'm saying? That's why this problem, I guess, is harder, is that you have to put those two forces there. You have two Coulombic forces. So you have an attractive force between the plus and the minus Q's. I'm going to call it F sub C, for FC here for Coulomb. Or maybe I should just call it, I'll just call it F sub C is all right. Okay, there we go. And then the other one is, now because the electric field is in this direction, going from right to left, that means you can think of it like, if this is the positive charge and it is going this way, that means it's attracted to the negative electrode or terminal here. So the force is going to be on this positive charge is going to be something like that. You see what I'm saying? Now I can call it F. I'm just going to call it QE. Is that okay? Where Q is the amount of the charge Q times E. You know, the Coulombic law. So I'm just going to call it explicitly QE. So these are the forces that I have on it. All right? And then, of course, this is the angle theta. All I need to do is to resolve the tension into components, and then I would work it out as usual. So in this case, I'm going to have, let me put it in a different color. How about green? All right. So here I'm going to have T sine theta. Is that right? And then I have T cosine theta. And of course, I could just ignore the T here, this here, because this has been replaced by those two. And then I would just work it out. So what I have here, sigma F sub x equals 0. The whole system is in a static situation. It's not, say, an oscillating pendulum or something. So in this case, you're going to have minus QE plus T sine theta plus F sub C equals 0. I got this equation. Watch your signs and all. And then sigma F sub Y equals 0. This will give me, what was that? Oops, let me go back to the diagram. I don't want to make it disappear. So here we have two of them. That's going to be T cosine theta minus mg equals 0. Again, I'm not interested in the tension, so I'm going to eliminate it. So T equal to mg over cosine theta. Now I take that and plug it back in there for T. You see what I'm saying? So when I do that, I mean, the rest really, I mean, we're done with the physics. The rest is just algebra. So when I do that, I'll end up with the following expression: minus QE, sorry, I keep making it disappear, minus QE plus mg tan theta plus F sub c equals 0. Now F sub c, well, what is F sub c? It's just a Coulombic attraction between them. Again, I'm just going to look at this diagram here, and then I'm going to make, from the triangle, let's assume that the distance between them is r, right? So with this triangle here, one of them, so that will be r over 2. Is that okay? And this one is, he said 0.5 meter, and the angle here is 10. So this tells me that sine 10 equals r over 2 over 1/2. Sorry, it's a little cluttered here. Let me go here. Sorry about that. Let's take it here. So that will be sine 10 equals, what is that? R over 2 times 2 over 1. That should give me r. Check it out. I think it's r. And then when you, with this, so sine 10, all you need is just to get sine 10, and it works out to be 0.174 meter. So that's the distance, 17.4 centimeter, okay? Now, go back to this equation right here, and plug in F sub c. Now, what is F sub c? F sub c is basically K Q squared, because they both have the same charge, over the distance between them. Is that right? And all I need is just to plug it in. So anyway, so this equation becomes minus QE plus mg tan theta plus K Q squared over R squared equals 0. And then I just need to plug in all the data here. Let me close the window. My neighbor is cutting grass. 1 second. Okay, and then we plug in the data that we have. The Q here is 100 nanometers. That's going to be 100 times 10 to the negative 9 multiplied by the electric field, which is 10 to the 5, plus the mass that we're looking for, G is 9.8, times tangent 10, plus, and now we come to the Coulomb's law, so that's 9 times 10 to the 9. Multiply this by Q squared, which is 100 times 10 to the negative 9 quantity squared, divided by the distance, which is 0.174 quantity squared, equals 0. And then be careful with your calculator. You may make mistakes. I made some mistakes when I was doing it yesterday. And anyway, so if you work it out, you basically want to you want to solve for m right here, and the answer that I got is 4.1 gram. Okay? All right. Next, the next problem has to do with, or let me just go back to the book. The next problem comes from my lecture notes. Oh, it's in chapter 23, not 22. I'm sorry. Anyway, it is similar to problems number 47 and 48. Let me show them to you in the book, from chapter 23. That is. So we go back. I'll go back now to the book, chapter 23, and the problems 47 and 48. Let me show them to you very quickly. I'm not going to do them. I'm going to do something very similar to them. Chapter 23. I believe one of them was a homework problem. Oops, this one here. There we go. So here what you have, here's 47, it says a charge Q is uniformly distributed along a thin flexible rod of length L. Here it is, see that? So it is a rod that is bent into a semicircle. The rod is then bent into a semicircle as shown, and then he wants to find the electric field at the center right here, okay? Now, you can do this problem after I do the problem that I have on my lecture notes. Very similar to it. And then the other problem, same thing, except that you have a quarter of a circle. I believe this is homework. I'm not sure. I think it is. It said a plastic rod with linear charge density lambda is bent into a quarter of a circle, okay? And we want to find the electric field right at the origin, okay? So I am not going to do that intentionally. I'm just going to do something very similar to them. You can really mimic the solution that I make if you want to practice those two problems, okay? So here it is. What I have, let me make the drawing first. So this is from problem for my lecture notes. What you have is that here's your, let's say we have same thing, we have a rod, and it is bent, and it looks something like that. I'll try to draw it, hold on. It's easy to draw on a chalkboard, but with that stylus thing, it's a little bit difficult. I hope the background is not noisy. Okay, so we have this, it's bent in this fashion. This is the x-axis. And then I have the y-axis right here. And if you draw a dotted line to both ends like that, the whole thing is symmetric, right? This is 60 degrees and the other one is 60 degrees. So that's 60 degrees and this one is 60 degrees. And the rod is bent into that shape and it is negatively charged. Okay, that's what makes it a little bit slightly different. Okay, so it's negatively charged, and I want to find the electric field right at the origin right here. Okay, at point P. Okay, so I have a rod bent of radius r. It's a plastic rod. The total charge on it is minus big Q, okay? And it is a third of a circle, as you can see. And the angles, of course, here theta or 2 theta is equal to 120 degrees, okay? I want to know what is the electric field at P. That's basically the question, okay? All right. What makes this problem different is that, first of all, it is negatively charged. So that means the electric field is not moving away from the rod, but it's actually towards it. In other words, if I'm going to draw a vector from point P due to the one end of the rod, it's going to look something like that. This is DE right here. You see what I'm saying? Okay. Also, the radius here of the rod is a constant. So notice that the radius r, let's just call it r, the radius r is constant. In other words, the variable here is really theta, okay? So how do we do it? Well, let's start with, okay, so if I take only an element of charge here, just like we did for the ring, dq, like that, okay? This is an element of charge. So this dq will equal to lambda ds. Make sense? What is ds? Well, let me give you another drawing. Same drawing, except I'm going to draw it geometrically speaking. Here is the rod right there, right? So if I take a portion of it, an arc, okay, this is a differential arc, if you will. That's going to be ds, and this arc has a width. Oops, sorry about that. I'm trying to make it better. Hold on. There we go, something like that. So this is d theta, and this is r, and the width of it right here is ds. You see what I'm saying? So in this case, you can say that ds is equal to r d theta. Remember, r is a constant. So this is important. You see what I'm saying? Okay. Now, we know that. Oh, one more thing. Notice that the dE here has two components, dEx and dEy, right? And because of the symmetry of the problem, see, if I take dE, let's say if I take another element here, the component dEy here will cancel with the component dEy here. See what I'm saying? In other words, dEy is going to look something like, whoops. dEy is going to look something like that, dEy. And then another dEy is going to look something like that. And they will cancel each other out. So the surviving term really is dEx. You see what I'm saying? We've done something like this when we covered the ring. So here, the only surviving component for the electric field is the dEx. So dEx is basically equal to dE cosine theta, right? And dEy all just they sum up to 0. Okay, the whole thing is 0. So back to the diagram. I'll put it in a different color. Hold on. Take a pink. So dEy is going to look something like that. dEx, like that, right? Okay. So what is dEx in this case? So dE, by definition, is what? Is k dq over r squared, right? We've done that before. So going back to dEx, so dEx will equal to k dq over r squared. Again, remember, r squared is a constant, cosine theta. Okay. Now, since dq is lambda ds, I can plug this one in there. Okay. So it becomes dEx equal to k over r squared lambda cosine theta ds. But ds is equal to, right there, r d theta. You see that? That's an arc length. So now this becomes dEx equals k lambda over r squared cosine theta times r d theta. Okay? See how I convert this equation from ds to d theta? Okay? Change of variable. And of course the r's here cancel out. I'll end up with, before I integrate, I'll end up with the following. K lambda is a constant, over r cosine theta d theta. That's dEx. Now I'm ready to integrate after all that. So I'm integrating from where to where? Well, first of all, I'm integrating with respect to theta. Well, what are the dimensions of theta? Well, it's equal to, a different way to do it, but one way to do it is to go from here all the way to here. So that would be from minus 60 degrees all the way to plus 60 degrees. Your math teacher would probably use radian, pi, from minus pi over 3 to pi over 3. You see what I'm saying? We'll just use 60 degrees, okay? So basically it's going to look something like that. So dEx is going to look like, first of all, let me kick out this out of the integral because the whole thing is a constant, right? So in this case, I'm going to have dEx equal to k lambda over r integral from minus 60 degrees to 60 degrees, right? Cosine theta d theta. You see that? What's the integration of cosine? It's a sine. All right. So in this case, I will have k lambda over r sine theta from minus 60 to 60, and then I just plug it in. So I have here k lambda over r sine 60 minus sine minus 60, you see what I'm saying? And that will give me, of course, sine 60 is 0.866, so that's going to be k lambda over r 0.866 plus 0.866, and then we finish the problem basically. So that will be equal to, if you work it out, you'll end up with 1.73 k lambda over r. And there we go. This is the electric field in the x direction. Again, the y direction is 0, right? Okay. Now, one more thing. What if I am asked to evaluate lambda? Okay. So I have that. How would I evaluate lambda in this case? Well, lambda by definition, lambda is equal to what? He said in the problem, let me go back to the top of the problem. He said the total charge on the rod is equal to Q. You may wonder why. It has to do with the fact that eventually we will be asked to evaluate lambda. So this is a number. The big Q here is a number, and we know that for lambda it is charged per unit length, and the length here basically the length of the rod, which is a third of a circle. So that will be the circumference of the circle, 2 pi r, divided by 3. So basically, what is lambda? Q over the circumference over 3. Make sense? So in this case, the lambda here is going to be lambda equal to Q over 2 pi r over 3, a third of a circle, right? And then we can take that and substitute it there. I mean, that's basically the value of lambda, given that we have a number, so we can just plug it in. Now, so how would the electric field E sub x would look like with this value of lambda, that is? And so that's going to be 1.73 k over r times, and if you work it out, 3q over 2 pi r, and the final expression, if you work it out, for the electric field E sub x is going to be equal to 0.83 q k over r squared. And if I want to put a direction to it, I can put it like that along the x-axis. And there we go. That's the final answer. Okay? Good. All right. The next one, we just jumped to chapter 23. I want to do number 73. 73 is kind of hard from chapter 23. There it is right here. Let me read it for you first. It's a challenge problem, as you can see. You know what? Let me do number 20. I wanted to do 72 as well. So let me do 72 first, and I'm going to do 73. So let's do it. They're both kind of a challenge problems. Okay, number 72. Okay, it says a proton orbits a long charged wire making 1 million revolutions per second. Okay? So you have a proton is orbiting a wire, a long charged wire. Okay. The radius of the orbit is only 1 centimeter, What is the wire's linear charge density, lambda? Okay? Sounds like a tough problem. All right. Again, always draw a picture so it will help you visualize how it looks like. Uh, 23.72. Okay, let's repeat the problem again, and then I'm going to draw the picture. You have a proton. It orbits a long charge wire, okay? And it makes 1 million revolution per second. That's basically 1 million hertz. That's a frequency. F equals 1 million hertz, all right? The radius of orbit is a whopping 1 centimeter, okay? That's very, very large for the subatomic world. What is the wire's linear charge density? All right. So let me draw a picture. So the picture looks something like that. Here is the wire. I'm going to draw it with a three-dimensional feel to it. Here's the rod. We can assume it's really long, okay? And it is negative or positive. I'll leave that for you. And here is the proton orbiting it. All right, here it is. Here is the proton orbiting it. This is the velocity, and it's going around like that. So it's going around the rod like that, okay? Now he's asking for what is the lambda. So now we said that the frequency is 10 to the 6 hertz, all right, revolution per minute, per second, excuse me. I'm trying to erase that thing. And the radius, I'll call it R. I'll call it big R, sorry, because it's a number, is 1 centimeter. And he's asking for lambda. Okay? Now, before I do anything, I know that whenever you have something going around something else, okay? Let's just review that very quickly from basic laws in mechanics. If I have something going around something else, say the Earth around the sun, or the electron going around the hydrogen nucleus, you know, which is a proton. Let's assume it's going in this direction, okay? So this is velocity, v. So it's going around because there is a centripetal force, F. And that centripetal force, centripetal means center-seeking force, like that. And the acceleration is also in this direction as well. The velocity is always perpendicular to both of them, all right? And this centripetal force is equal to ma, but a here is a centripetal acceleration. This c means centripetal, not Coulomb. So that's going to be the mass of the electron times the velocity squared over r, r being the radius of the orbit. You got that? Make sure that you understand that. If you've never seen it before, I'm sure you have. But make sure that you understand. Whenever you read something going around something else, this picture, this equation should come to your mind immediately, okay? Immediately, this equation should come to you. That's basically because it describes an object going around something else. And the reason why is it going around something else? Because of this force right here. That force, what we call a centripetal force. It takes different forms. It could be Coulombic force. Could be gravitational force. It could be whatever. It could be whatever kind of force. But it's a force. As long as it is directed toward the center of the orbit, the object is going to go with a circular fashion. Okay, circular orbit. It's going to follow a circular path. You see what I'm saying? Okay. So that's what I have in mind when I first read this problem. That's the first thing that occurred to me. Okay, so it's similar to something like that. So I need to apply this concept to my problem, all right? So here is the orbit, call that. I'm sorry for the lousy drawing. I am a much better, more talented guy when it comes to drawing stuff like that, but with this stylus pen, I'm not doing well with it. Anyway, so here is the radius of the orbit, r, right? And it's going around. So basically what I have in here is this picture in my mind. I want to use this, where it is F equals ma. M here is the mass of the proton. You see what I'm saying? It's the mass of the proton. And A here is the centripetal acceleration. Simply m v squared over r. That's really what it is. And then I have the F here. the F here is what's causing the object to orbit. Well, what's causing it to orbit? Obviously, it's the Coulombic force. Makes sense? Okay, you have the rod, and then you get the proton. They're both charged. It's not because of gravity, right? And of course, the rod, I hope you already know that, the rod should be negatively charged, right? Otherwise, it's not going to orbit. It's going to be repelled. So there we go. Okay, it's going to be negatively charged. So there is a Coulombic attraction between them. And that Coulombic attraction is acting like a centripetal force, like that. Okay? And that centripetal force, well, where is it coming from? Well, it's coming from the field. From the field that the rod is giving off. Okay? Is emanating from the field. And that field, since it's an electric field, and that electric field should equal to QE. What is Q here? Well, that's just the charge of the orbiting particle, right? This is the charge of the orbiting particle. Well, it happens to be a proton, so therefore this is the fundamental charge. So now I can write it this way: EE equals mv squared over r. Okay? You see how I'm developing my ideas slowly, one step at a time. I'm reading my mind for you, or speaking loudly what my mind is thinking. Okay. The next step is, all right, so I know what E is. That's no problem. I don't know V, but he gave me a hint. Look at that. He gave me the frequency, and I know I can find the velocity if I have the frequency. I'll tell you about it in a minute, but that's not the issue now. That's not the hardest problem. The hardest problem is the E. How in the world am I going to get that E? Well, we already did that. We did it. Actually, we will do it in chapter 24 when we cover Gauss's law, but in chapter 23, let me show you where to find it. It's on page, let me find it in my hard copy. And I believe I referenced it to you before. Hold on, let me find it. Sorry. It's in there. There it is. Nope, not this one. There it is. It's equation 2317. I'm going to show it to you in a sec. Equation C 2317, page 639. I'm going to show it to you. I already showed this equation to you in a previous video. So let me go to it again. Section Section 3. Here is the rod. Remember that example 23.3 right here. This is the example right here. This is example 23.3 right there, and then he goes on and on and on a couple of pages, and down the line he gives you the equation right there. He said the electric field due to a long rod of infinite length. Remember this one? And we did it in Gauss's law. Remember that in chapter 24 video lecture? Well, that's the formula we're going to use, and he's asking for lambda. Well, it's right there. Do you see how simple the problem becomes once you are aware of those things? So that's the equation I'm going to use for the electric field. That's basically the electric field right here, instead of saying. So what it is, so let me write it down. So the electric field due to this rod is basically E equals to 1 over 4 pi epsilon naught 2 lambda over r. R here being the radius. The radius of that orbiting thing, the orbiting path, okay? So now I have all of that. I'm going to take this thing and plug it in there, and let's do it. So in this case, I'm going to have E over 4 pi epsilon naught 2 lambda over r equals to mv squared over r, okay? The r's here Unless I made a mistake. Did I make a mistake so far? No, I did not. Okay, let me stop right there. I want to do something else. Look at the velocity. We know that the velocity is equal to omega r. Remember that when it comes to circular motion, where omega here is the angular frequency or the angular velocity. Is that right? And I know that omega is 2 pi f. F here being the frequency, which is given to us. So I can plug it in there. So the velocity in this case is going to be 2 pi f r. See that? So now I can take this as well and plug it in there. Okay? So let's do that. So the r's here cancel out. I hope I'm not messing up my algebra. So I have here 2e lambda over 4 pi epsilon naught equal to 2 pi m f r, sorry, I have to square it. Let me do it again. So let's have an m here, and that's going to be 4 pi squared f squared r squared. You see that? And remember, I am solving for lambda. So in this case, if I solve for lambda, that's equal to, oh, okay, you get this to be 2. If I work it out, I'm going to end up getting this, 4 pi epsilon naught m 4 pi squared f squared r squared over 2e, and there we go. Then you clean it up a little bit. If I look at if I look at it, if I simplify that, you'll end up getting the following: 2 pi. I'm copying this for my notes. I only have brief steps here in the notes, but anyway, if you do it, you'll end up getting that. K here, of course, is 1 over 4 pi epsilon naught. Okay, then you have that. There we go. Here is your linear charge density, and we just plug in everything. We have everything so far. So we have lambda is equal to 2 pi squared, the frequency 10 to the 6 squared. The radius, he said, is 1 centimeter, so that's 0.01 squared. The mass of the proton, I would encourage you to memorize it, 1.67 times 10 to the negative 27 kilogram, divided by EK. E is the fundamental charge. Please memorize it, especially if you specialize in electrical engineering. 1.602 times 10 to the negative 19. Multiplied by K, 9 times 10 to the 9, and then you calculate all of that. The answer that I got is 2.28. Check my work, please. 2.28 times 10 to the negative 9 Coulomb per meter. All right, and there we go. Okay. Okay, good. Let me see if I miss any problem. Oh yes, if we want to do it, we still have one more problem, and that is number 73. All right. Before I talk about 73, I want to review with you what is meant by SHM, simple harmonic motion. Harmonic motion. This is a very important concept in physics, and so let me tell you what it is, or remind you for those of you who already studied that. A simple harmonic motion is basically an oscillatory motion or a vibrational motion where the object is going back and forth or to and fro, but with very, very small amplitude. For example, let's say I have a pendulum, Here is the pendulum. Here is the string. Here is the bob. And let's say it's not oscillating, it's just hanging there, okay? Then I give it a small push, okay? So what happened that the pendulum is oscillating like that. Just like the grandfather clock, okay? So it's oscillating. Let's assume that the angle here, say 20 degrees, okay, for example, okay? Is this an example of SHM? No. Why? Because the angle is too large. The SHM oscillation, the simple harmonic, remember the word simple harmonic or harmonic motion means vibratory motion, oscillatory motion. That's the meaning of it, okay? Just a fancy term for that. The word simple, I'll tell you what that means in a second, why we use the term simple. Okay, so the word harmonic or simple harmonic motion means that the oscillation is so tiny you could hardly see it, okay? You know, think of it like when you have your phone, you put it on vibration mode, okay? Now, if it is, let's say you're holding the phone in your hand and it is somebody's calling you, now it's it's vibrating, right? You can feel the vibration in your hand, but you don't see them because the amplitude of the vibration is extremely tiny. You see what I'm saying? That's a good example of SHM. Okay, so in other words, the oscillation is very, very small, the amplitude of the oscillation. So a pendulum is oscillating in SHM would be something like a pendulum where the angle or the angular displacement of that pendulum would be something like, say, 5 degrees, 2 degrees, 3. I mean, 5 degrees will approximate it, but 1 degree would be great, or even half a degree. You can hardly see that oscillation, okay? This is very important. Why is it important? Well, in such case, if you have a system that is vibrating or oscillating with small amplitude, then the force that is causing this vibration, we call it the restoring force, is equal to kx or minus kx. Okay, I'm sure you've seen this formula before, but probably your high school teacher taught you, well, this is just a spring, the spring force. This is where k is the spring constant. Yes, but it's much more than that. It's much, much bigger. This formula applies to anything that oscillates, anything at all, anything that oscillates, where k here is what is called the, we can call it the vibration constant or the oscillation constant, excuse me, okay? For the case of the spring, we call it the stiffness constant or the spring constant, okay? Okay, so it's called the spring constant. I like to call it, for the spring, I like to call it the stiffness constant. It tells you how stiff the spring is. But that's not our subject, really, the spring thing. But what that means, let me just elaborate a little bit more on this formula, on this equation, F equals kx. Now, the minus sign here, it means it's a restoring force. That means it repeats itself over and over and over again. Okay, it's a restoring force. So that's the restoration itself. Restoring. Okay. Any object, okay, any object at all, it doesn't have to be a spring. This is important. Any object that oscillates, okay, and the oscillation where x here, the displacement, is very small, the amplitude is extremely small, so x here is very small, then the force here, the force law, approximates SHM. Got it? However, if the oscillation is very large, say a pendulum also swinging with 20 degrees or 30 degrees, that's not SHM at all. And this formula, F equals kx, does not apply to it. You get that? This is important. Now, let's go to the problem, and I will elaborate on this important formula when we solve this problem. That's why I wanted to do this problem. Such a cool problem, because it teaches you other things beside the actual statement of the problem. All right, so it is on chapter 23. I need to go back there. 23, question number 73. Okay. Let's read it together. He says, you have a summer intern position with a company that designs and builds nano machines. An engineer with the company is designing a microscopic oscillator, okay, a microscopic oscillator, to help keep time, and you have been assigned to help him analyze the design. He wants to replace a negative charge at the center of a very small, positively charged metal ring, okay? His claim is that the negative charge will undergo SHM at a frequency determined by the amount of charge on the ring. Aha! Isn't that interesting? So when I read this problem, and with this background that I have just told you about, that means what? If it's going to go SHM, that means the oscillations here are really small, very, very small, okay? That's the meaning of it, because it cannot be SHM. Oh, I forgot the word. Simple here means it's a very, very small oscillation, okay? And simple as well, it means that it can be described by this simple formula, F equals Kx. Got that? That's the meaning of it. All right. Part A. He said, consider a negative charge near the center of a positively charged ring centered on the z-axis. Show that there is a restoring force on the charge if it moves along the z-axis but stays close to the center of the charge. See, it stays close. That means the oscillation is really tiny. That is, show there is a force that tries to keep the charge at z equals 0, which means what? What does that mean? He said, show there is a force that tries to keep the charge at z equals 0. What he's saying here, show that this force is a restoring force. You got that? So he's really talking about this equation, but he didn't tell you that explicitly. Okay, he's saying that, show that, well, we want the oscillation to be really small, which means x here is really tiny, and show that this force is a restoring force. So basically he says, show that this force is F equals Kx. Now remember, as I said, F equals Kx could apply to any SHM motion, where this K right here, guys, is not the spring constant. It could be something else. For example, it could be F equals to, you know, some stuff here, whatever the nature of it. But the important thing is that it is linear in the displacement. X, not x squared, not x cubed, whatever. It is linear in the displacement. Okay? That's the meaning of it. So F of x here is linear in displacement. Okay, it's not quadratic or whatever. Got it? That's what makes it so special, this force. All right. So how do we do something like that? Well, let me draw a picture of it. I'm going to jump to this to a new page here. Number 73. I'm going to draw the picture for you. Here it is. Here is the ring. Try to make it 3D as much as I can. There we go. And the ring is positively charged. I'm going to put little pluses here and there. Okay, and here is the x, he said the z-axis, whatever, x or z. I'm going to call it x-axis. There it is. This is the x-axis. Let's say it just extends both sides like that. And this is the radius of the ring right there. Since the radius is constant, I'm just going to call it big R. And then you get this little particle that is oscillating to and fro like that. You see what I'm saying? There it is. And this particle is negative. We are saying that this particle, so it is oscillating back and forth. It's just one particle. It's not two particles. You got that, guys? I mean, here is the ring. Let me draw another picture. Here is the ring. That's kind of a two-dimensional flat picture. And right at the center, we have this negative particle is moving like that to and fro, very close to the origin of the coordinate system. Okay, so that's basically what we have. And he's saying, show that. What he's saying is this, in plain English, show that F is equal to something, some constant, times X. That's really what he's telling me. I want to get this formula. This is the formula that I'm looking for. Here, let me read the problem again for you. Consider the negative charge near the center of a positively charged ring. Show that there is a restoring force, F, on the charge, and it moves it along the z-axis and stays close to the center, which means the x value here, or z value, is very small. And that shows that there is a force that tries to keep the charge at c equals 0. Okay? How do we do this problem? Well, first of all, we have done the ring problem, you remember? And I don't need to show you where in the book what is the ring problem, the equation for the ring. But here it is. If you go back to my notes in my video lecture, where the ring problem, so go back to the ring problem, where I solve it in details, and we said that E is equal to 1 over 4 pi epsilon naught x q over x squared plus r squared to the power of 3/2. What does that mean? With the ring problem that we solve, it looks something like that. Here is the ring, here is the x-axis, and we want to find the electric field here due to the ring. So we picked some element here, remember that? And so we have the dE here. So we got dEx and dEy. The dEy cancel out, remember that? And then we integrated along that, and then we ended up getting, well, this is the distance x right here from here to here. So I'm saying, and that's the radius of the ring, big R. This is how we did it. Go back to the notes, and you'll see it there. Okay? So, and then we ended up getting the ring equation, which is right here. Okay. Well, how is this related to ours? Well, what's causing the charge, the negative charge here, to oscillate to and fro? The force, right? The restoring force. And what is the restoring force is equal to? Well, it's equal to Fx. I'm hoping to get that Fx, but I know it's the restoring force, okay? Well, what's the nature of that restoring force? Well, it is Coulombic. I mean, obviously it's Coulombic. You have a negative charge here, and then the ring is positive. What's causing the oscillation is really a Coulombic force. Well, what is the Coulombic force is equal to? Well, I got the electric field, so therefore the Coulombic force must be QE. See that? So here the force is F equals QE. I can put a minus sign there because I am kind of excited it's going to be a restoring force, but let me ignore it for now. You can put it there if you want to. I'm trying to erase the thing. There we go. Okay. So now that's going to be equal to, again, go back here and plug this E in here. Remember, this Q is for the oscillating negative charge right there. This charge right here is small q, and the big Q is the charge of the ring. Instead of saying that's the big charge and this is small q. So in this case, I'm going to have, again, copying this thing in there. So I'm going to give me 1 over 4 pi epsilon naught QQX over x squared plus r squared to the 3/2. I have that. Okay. Now he said the oscillation. He said, but since oscillations are too small, what's the consequences of that? Well, if the oscillation is too small, look at it. Let's go back to the picture. Here. So the oscillation here is the value of x right here. You see what I'm saying? It is x right there. Compare it with the radius of the ring. The ring is huge compared to this oscillation. Okay? Extremely large compared to this oscillation. What does that mean? It means, because it is really close to the center, this means that r squared, or r, is much, much greater than x, or rather r squared is much, much greater than x squared, which means that x squared plus r squared is almost equal to r squared here. This and the denominator right there. Okay? So when I do that, what do I get? So I want to use this approximation to work out this one. So in this case, I'm going to have F. Again, I am excited to put that minus sign just because it's restoring. So I'm going to put that minus sign there. So I have here minus, and I am here. I'm going to take that and put it in here with this approximation. So I'm going to get 1 over 4 pi epsilon naught Q x over R squared quantity 3/2. This gives me, let me put it in another page here. So this gives me F is equal to, well, what is that? R squared to the power of 3/2. That's just going to be R cubed, correct? So let me collect everything together. So I'm going to have minus, look how I'm going to write them down. Q, big Q, over 4 pi epsilon naught R cubed, close that, times X. Look at that. Now what is that? That's definitely SHM. Do you see it? Do you see the SHM? F equals minus Kx. The K here, again, your high school teacher would call it the spring constant, but it is really oscillatory constant, the oscillation constant. It's for, it just basically describe the oscillation here, how rapid the oscillation is, how rapid or how slow it is, okay? So there it is right here, okay? That's the K, the oscillation constant right there. This is definitely X linear, which makes it a, and this, of course, the minus sign, I just imposed it. This is a restoring, and there we go, we have that. So go back to the question again. What did he say? He said, show that there is a restoring force on the charge. Aha, there it is right there. Okay, so we have just proved it. Okay. All right, part B. That's I like this problem because of the you know, it's rich with concept. It's just so much, you learn so much outside what you are studying in this chapter. All right, the next part. Oh, by the way, I have a little exercise for you. You don't have to do it, but I have an exercise for you. There is the approximation that we use here is this one right here, and it is a legitimate approximation, no problem. But here is a fancy way of writing it. See, if X is much smaller than 1, then 1 plus X to the power of N is almost equal to 1 plus NX. Okay? Here is your exercise. Use this approximation to arrive at this force. In other words, start from here, right here, or rather actually just the bottom, the denominator. X squared plus R squared to the power of 3/2. Okay, here, let me just give you a little hint. Start here, X squared plus R squared to the power of negative 3/2. I just put it on the top, okay? So I'm just going to move it to the top. This is the denominator. I'll put it in the numerator. You see what I'm saying? So if I just take that thing and move it up here, ignore everything else. Just ignore that. Just work on this, only this denominator right there, okay? Here it is. Now, take this one and compare it with this part right here, and then use this approximation right there to show that you will arrive at the same result here, this one. Okay? Go ahead and play with it, and if you are curious, you know, send me a, I mean, you can post it at Ask the Professor, and I will grade it for you. I'm not going to give you credit for it. Just, you know, just a little exercise. If you know how to do it, post it at Ask the Professor. And if you don't know how, I'll be more than happy to show you this approximation. Okay, part B. Now, part B says, he said, show that for, show that for a small oscillations, which is that what we have proven, with amplitude much less than R, which is the value of x, a particle of mass m and charge negative q undergoes a simple harmonic motion with the frequency. Basically show that the frequency is equal to that. Okay? Show that this is the frequency. Okay? You can pause the video, look at it, or write it down before I show you how to work this problem. So I have a frequency is 1 over 2 pi square root of QQ. Okay? The big Q is the charge of the ring. The small q is the charge of the oscillating thing. And then I got 4 pi epsilon naught, the mass of the particle, and the radius of the ring cubed. Got it? Okay. How do we do it? Well, whenever you are dealing with SHM, okay, you ask the question, you know, because it is SHM, that means it is oscillating like that, okay? There is a legitimate question. You ask, what is the frequency of oscillation? In other words, how many excuse me, how many cycles per second, or how long it takes it to make one cycle? You got that? One of them, how many cycles per second, that's called the frequency, and how long it takes it to make one cycle, that's the period. And of course they're both related to each other. The frequency is 1 over the period. Okay, the frequency is number of cycles per second, right? And the unit of it is hertz. And then the tau, which is the period, period, I can't spell it, is the time to complete one cycle. You got that? All right. So he said, show that the frequency is given by this equation right there. Okay? Well, how do we do it? Well, in general, when I have SHM and I have my force is equal to minus kx, I'm talking here in general, where k here is the oscillation constant. Okay, whatever it is. For the spring, you know what it is, just a stiffness constant, and so on. The corresponding frequency, again, I can look it up from my book. The corresponding frequency has always been 1 over 2 pi square root of k over m. Where does this come from? It comes from the differential equation that describes the oscillation. Okay, that's kind of advanced mechanics, but it should be in your book. Or you have studied it, hopefully, in Physics 180. That's basically what it is. Where k here is what is the spring what we call the spring constant or the oscillation constant, and of course m here is the mass of the oscillatory. The mass of the oscillatory mass, if the mass of the oscillatory particle or whatever it is, okay? So I want to use this formula to get the frequency. Now, before I go any further, go back to the equation right here. What's the value of k? Well, here is the k right there, okay? Here is the k. QQ, 4 pi epsilon naught r cubed. That's the value of k. And all I need to do is to take this k and plug it in here, and I think you should be done with this problem. It's really simple. So that's going to be 1 over 2 pi, big square root of k. What is k now? I hope you've written it already. That's going to be QQ over, I'll show it to you again, 4 pi epsilon naught r cubed, 4 pi epsilon naught r cubed. There we go. All you need to do now is just to kind of clean it up a little bit. Maybe you want to insert this 2 pi in there. It's going to be 4 pi squared in there, instead of saying. And when you do that, you'll end up with oh, I forgot the mass here. Sorry, there is a mass here, right? So there is a mass, m, right there. And when you work it out, you'll end up with, I mean, that's basically, let me compare it like this. Maybe this is the last step. I'm not sure how he put it. There we go. 1 over 2 pi QQ 4 pi. There we go. Yeah, this is it. I don't think I need to do anything else. There we go. Simple. Okay, good. Part C, I think I'm going to leave it up. I'll leave it to you to do it. He said evaluate the oscillation frequency, this one right here, for an electron. So the mass here is an electron, 9.11 times 10 to the negative 31, at the center of 2 micrometer diameter ring. Okay, so remember, this is the ring. Remember, this is nanotechnology, so everything is really tiny. So the ring is 2 micrometer. Okay, 2 times 10 to the negative 6 meter. That will be the diameter divided by 2 to get the radius, a big R. And the ring, and the big Q here, of course, is 10 to the negative 13 Coulomb. And of course, the small q here would be the fundamental charge of the electron, 1.602 negative 19 Coulomb. Just plug it in, you get that frequency. Got it? Okay. All right. Is there anything else? Oh, yes. Now we move on to, I'm sorry, there's one more problem. Number 59. Yes, the Bohr model of the atom. Let me do that. 59. Simple problem, I hope. I'm going to go over it very quickly. There we go. Just a level 2 difficulty. He says, in a classical model of the hydrogen atom, the electron orbits the proton in a circular orbit of radius, which is called the Bohr radius. Okay, this is the Bohr model of the hydrogen atom. He got the Nobel Prize for it, actually. So anyway, so he said the Bohr radius is 0.053 nanometer. He said, what is the orbital frequency? What's frequency? It means the number of cycles per second. Remember that? We talked about that. The proton is so much more massive than an electron that you can assume the proton is at rest. Okay? All right. How do we do it? Simple. So what's the picture? Again, the picture is basically the classic picture of the hydrogen atom, or the Bohr model of the hydrogen atom. We have the electron here, and it is orbiting in this direction. Oops, let me just put, here is the proton right here, much more massive. If you want a comparison between a proton and the electron, they both have the same charge, as you know. They both have the fundamental charge E. But a comparison in terms of mass, think of a basketball and a dust particle. Okay, a dust particle right at the tip of your finger, you could hardly see it. That must say it's white color. So that's this white dust particle right there, and compare it to the size of a basketball sitting beside it. That's the ratio of the mass of the electron, or the size rather, the mass or the size of the electron and the proton. They're huge, the proton, compared to the mass of the electron. But they both have the same charge, the fundamental charge. Okay. All right. So he said the Bohr radius, I'm going to call it, the symbol for the Bohr radius is A naught in modern physics, so I'm just going to use that. 0.053. To be exact, it's actually 5.29 times 10 to the negative 11 meters. Okay, that's the Bohr radius. So here's approximating it, nanometer here. Okay. He wants the frequency. I think we did this before. How do I get the frequency? Well, as I said before, we know that the velocity, remember this electron, let me use my mouse, the electron here, it makes one cycle. The time it takes it to complete one cycle is the period, right? So the velocity of it, let's assume the velocity, I'm talking about velocity here. The velocity of it is the circumference of the orbit divided by the period, by the time it takes it to complete that circumference. So basically 2 pi A naught being the radius, the Bohr radius, divided by the period. Okay, but we said that the frequency is 1 over the period, the reciprocal of the period. So therefore, the velocity is 2 pi A naught F. See that? Okay. And so therefore, F is equal to the velocity over 2 pi A naught. What's more than that? Anything else? How do I find V now? You can pause the video and think about it. But again, go back to the picture. As I told you before, whenever you see something going around something else, think of centripetal acceleration and centripetal force. Of course, the centripetal force here is nothing but the Coulombic attraction between them, right? And that Coulombic attraction is F equals ma. M here is the mass of the electron. F here is the Coulombic force, so that's going to be K Q1, Q2, which is E squared for both electron and the proton, divided by the Bohr radius squared, is that right? Equals the mass of the electron times A here is the acceleration, which is V squared over the Bohr radius. You got that? Make sense? And all I need to do is to solve for V, because I am trying to get rid of the V, and just plug it back into the frequency here, and I'm done, really. So solve for V here. If I do it just by very quickly like that, so of course the A's will cancel out here. So that's going to be K E squared over A naught M for the electron to the power of half, right? And then I take that, plug it back in there, and therefore the frequency in this case is going to be equal to 1 over 2 pi A naught K E squared over A naught M sub E to the power of half. And there we go. That's the frequency. Plug it in and get the answer. Got it? Okay. I'll stop here as far as chapter 23. I think I've done them all. Now let me move on. I have one more problem to do from chapter 24. It's kind of a toughy one. Do not expect it to be on the exam. I promise you that. It is basically the case, and I think I mentioned it in the video lecture, where when the charge density is not constant, we always assume the charge density is constant because it is for simplicity. But I'm sure for those of you who are majoring in electrical engineering, you're going to be taking an advanced course where what if the charge density is not constant, which is a lot of time it's not constant. So what do you do? How do you do that? So I picked a simple problem. There are like 3 problems that talks about this case, but I picked one of them, and they are at the back of the book. I believe the last 3 problems in the chapter. Problem number 61, 60, and 50, and I'm reading them from my hardcover, 59 and 58. These are all problems that deal with the charge density is not constant. I picked the easiest one that was relatively easy, or at least more interesting for me, which is number 60. Okay, so I'm going to do number 60 from chapter 20, number 60. Yes, number 60. Okay. Let's go over it. Chapter 24. I'm sorry. 24. 24. That's right. Number 60. All right, there it is right there, level 3 again. He says a sphere of radius big R, okay, so this is a constant, has a total charge big Q. Remember that the big Q also is a constant. So they both have, the sphere is not losing charge, or the sphere is not getting smaller or bigger or whatever. All right, the volume charge density, Coulomb per meter cube within the sphere is given by that. Look at that. So the volume here is, okay, rho naught is a constant, the big R is a constant, but you have this R. So in other words, as you go from the center toward the edge of the sphere, it's varying, it's changing. Okay, the value of it is changing, and it's changing basically. It's increasing because it's linear in R here, so it's increasing in value. See what I'm saying? Linearly, it's increasing linearly in value as you go from the center outward all the way to the edge of the sphere up to big R. You see what I'm saying? this charge density, I'm sorry, decreasing because of the minus sign. See, this charge density decreases linearly from not at the center to 0 at the edge of the sphere. Okay, now it's increasing actually in magnitude, but in terms of, but because of the minus sign, so it's getting more negative. So that's why you put it decreasing. Okay. So anyway, but if you would ignore this minus sign and make it say a plus, it's actually increasing linearly. Make sense? Anyway, so we have that. He said, so this charge density decreases linearly from rho naught at the center. So the value at the center, you can actually prove it to yourself. If you make r to be 0, the small r 0, so at the center is r naught. Then at big R, it's going to be r. So yeah, big R here at the edge. So r over r is 1. So 1 minus 1 is becomes 0. Okay. So here we have this charge density decreases linearly from r naught to. Okay. Show that rho naught is equal to 3q over pi r cubed. Part B, show that the electric field inside the sphere points radially outward, and that is the electric field that is associated with it. And then show that your result of part B has the expected value of that. Okay, so let's solve this problem. Okay, how do we do it? First of all, let me draw a picture. Problem. Let's do chapter 24. Problem number 60. So a picture would look something like that. So I have this sphere. We are assuming it is a solid sphere. It's not a spherical shell. And that is charged all through it. So that's like an insulator, if you will. And so what I want to do, I want to draw a spherical shell at some arbitrary radius, small r. Okay? So here is the center of it. Here is the spherical shell right here. Not a spherical ring. Excuse me, not a ring. Oops. A spherical shell. And let's assume that spherical shell here has a thin thickness. We're going to call it dr. I'm trying to make it as thin as possible. Bear with me. There we go. Where this is dr. Okay? And the radius of it is small letter r. Of course, the radius of the sphere, this is the whole sphere, it's big R. You got that? And of course, this spherical shell. Now, if the total charge on it is big Q, so the charge on this spherical shell is going to be, let's say, dq. Is that okay? Just like we've been doing in the past when we were covering Gauss's law. Okay? All right. Now, he says, let me just write what he said. He said that for part A, he said the charge density rho is equal to rho naught 1 minus r over big R. Okay? He said, part A, he said, show that rho naught is equal to 3 big Q over pi r cubed. Okay? So let's take that spherical shell, the one I just showed you here, the one that's shown in the diagram right here. Okay? What is the differential volume of that spherical shell? Well, it's basically the surface area times the thickness, right? It's the surface area of the spherical shell times the thickness, which is dr. So the surface area of a sphere is 4 pi r squared times the thickness dr. So that would be the differential volume. Make sense? Now, we know that, again, this is this differential charge for that spherical shell. In other words, just to remind myself that this big Q is basically the integration of dq. See what I'm saying? And this dq, by definition, what is dq? Let me take that. But dq by definition is rho dv, correct? You can pause the video and think about that, but we did this before. You know, rho is dq over dv, charge per unit volume. Well, there it is in differential form. Okay, so now I can take this and put it back into the big Q. So big Q here is going to be equal to the integral of rho dv. Okay, now we just said that dv is equal to 4 pi r squared right there. Okay, and of course the rho is right there, so I'm going to put both of these here. Okay, so if I work it out, I'll end up with this integral of, for the dv is going to be 4 pi r squared rho dr, and that's the first step. Second step, of course, I'm integrating from where? I'm integrating, go back to the picture. I am integrating from 0 all the way to big R. See what I'm saying? So that's going to be from 0 to R. 4 pi r squared rho. Well, what's rho? Go back to the book. It's rho naught 1 minus r over big R dr. All right? That's the one right there. That's rho right here. And there we go. I am ready to integrate. Of course, rho naught here is a constant. 4 pi, of course, is a constant. Take them out. Clean it up a little bit. So I end up with this. 4 pi rho naught from 0 to r. Let's see. R squared minus r cubed over big R dr. Right? And then I integrate. 4 pi rho naught, integrate simple, so that's r cubed over 3 minus r to the 4th over 4r from 0 to r. Plug in the r in there, so that's going to be 4 pi rho naught r cubed over r over 3, excuse me, minus r to the 4th over 4r. That gives me 4 pi rho naught r cubed over 3 minus r cubed over 4. Simple, just 1/3 plus 1/4. And that would be what? 1/12, is that right? So that's going to be 4 pi rho naught r cubed over 12, I think. From, oh, I forgot to put the limit, 0 to r, 0 to r, 0 to r. And then we'll plug in there, and then I will end up with, so that will be, again, we are solving for big Q, remember? All these equals are basically big Q right there. So this, therefore, big Q is equal to, that's basically an expression that that describes the total charge. And that's going to be 4 pi rho naught r cubed over 12. Okay? One more step, because I have the 4 and the 12 here. I forgot about them. So that's going to be pi rho naught r cubed over 3. That's basically big Q, right? He's not asking me for that, I know. Now, therefore, rho naught is equal to, trying to erase that thing, it's not erasing, there we go. Rho naught is equal to 3Q over pi r cubed. And there we go. Is that what he said? Go back. Shouldn't have moved that thing, but anyway. Yeah, we got the same thing, okay? There we go, okay? That's the first part of the problem. Now the second part, part B, he says, show that the electric field inside the sphere points radially outward with this magnitude. Okay, so we have this magnitude of the electric field. When I'm asked to find the electric field, the first thing that comes to my mind is Gauss's law. So I'm going to do Gauss's law here. So the way I'm going to approach it, basically start with Gauss's law. So he says here, show that. I'm going to copy it from the hard copy here. So that he said E is equal to QR over 4 pi epsilon naught R cubed. This is for rho naught. You see what I'm saying? 4 minus 3R over R. Okay, show that. Well, how do I do it? Well, let's start with Gauss's law. So I have E dot dA equals Q enclosed over epsilon naught. Okay. Now the main difference what I have done in part A and part B is that in part A I have gotten the entire total charge. I've done all of that, all this long calculation to get the total charge. Okay, an expression for the total charge. Okay. I'm going to do the same thing. The only difference is that because I want to get the enclosed charge for Gauss's law, so it's not going to be from 0 to big R. It's just going to be 0 to some arbitrary small r. You see what I'm saying? You know, the radius of the Gaussian surface. This is important. So basically, I'm going to carry the same integration for the Q enclosed, except that this one is just to small r, not big R, because that's just the radius of the Gaussian surface. In other words, Q enclosed here. So first of all, the left-hand side is relatively easy. So it's basically E times 4 pi R squared, you know, the surface area of that Gaussian surface, equal to Q enclosed divided by epsilon naught. Now I need to find Q enclosed, which is basically the charge, not the total charge, only the charge of the Gaussian, the charge enclosed within the Gaussian surface. Okay, and that Gaussian surface has a radius small r. You see what I'm saying? So in this case, the enclosed charge, it's just going to be exactly the same expression that I have written above. I hope you've been taking notes. You can look at it, and that's equal to, from 0 to small r, you know, the radius of the Gaussian surface, 4 pi r squared rho dr, where this rho is what we have, what's being given to us, you know, that not constant rho, the one that is non-uniform. So I'm going to plug it in there. So that's going to look something like that. So the charge enclosed is equal to, from 0 to small r, 4 pi r squared rho naught 1 minus r over big R dr. See that? And that's it. It's really not that bad. All you need to do now, you just carry the integral. The integral is identical to what we've done above. The only difference is that the limit of the integration is a little bit different. It's a small r, not a big R. You see what I'm saying? And when you work it out, so you work out the integral. So Q enclosed, you will arrive at this expression. I've done this problem in the past, so I'm copying it from my notes. And there we go, which is basically what he's asking for. Right there, this one. Okay? He says show that, and we actually got it. Okay? I'm sorry, this is just for the Q enclosed. I'm sorry, I'm a little bit ahead of myself. So therefore, E, go back to this equation right here, and solve for E. And then, of course, I already have Q enclosed right to the bottom right here, and then I just move this to the other side and I work out for E, and then E, I will get the value for E is equal to, you know what, I think I have done, sorry about that, this is the E here. I am looking at my notes and I think I copied the wrong thing, so this is E right here. Okay, so basically, let me just recap. I hope I didn't confuse anybody. So you start with Q enclosed. Here it is. Go through the integration. You will get, I'll give you the answer. Here it is. The Q enclosed is going to be 4 pi naught r cubed over 3 minus r to the 4th over 4r. And then you take that, go back to the equation, the Gauss law right here, to start, plug it in there, and then you solve for E. See what I'm saying? You work it out, you'll end up with this. Okay? Now, part C, I'm almost done. Part C is pretty easy. He says, show that your result of part B has an expected value of at r equals big R. Well, you can work it out. You're basically going to get the point charge. Okay, you can work it out. You'll get this. E equal to 1 over 4 pi epsilon naught big Q. Okay, I think I'm going to stop here. I hope this has been helpful. I apologize if there has been any noise, background noise. My neighbor is still cutting grass. But anyway, good luck on your tests. If you have any question, please let me know. Goodbye. Bye.